The Task Parallel Library, the TPL, has been around in the .NET framework since version 4. The TPL is designed to make it easy for you to work with threads and asynchronous operations, so you can run work in parallel or asynchronously and not have to worry about partitioning work and scheduling threads and some of the other low-level details we've always had to worry about with threads in the past. Although the TPL is very good at a number of things like parallel processing, we're going to focus on using the library for asynchronous processing. On the web server, we're usually not as interested in parallel processing as we are in keeping request threads busy, which if you think about it is already a form of parallel processing because multiple HTTP requests can be executing in parallel. But to keep these server threads busy, we need to offload some input-output work, some I/O work, make it asynchronous so that we don't block the request processing threads and make them sit idle. We're going to do this using one of the features of the TPL, which is the task class. Think of a task as this, as a representation of work that needs completed by some point in the future. So it's a representation of work. You can encapsulate operations and asynchronous operations in a task and then make them execute synchronously or asynchronously or in parallel. You can combine tasks together, combine tasks with a callback, manage state across tasks. You can do all sorts of wonderful things through an API that makes the complicated things easy. Let's take a look in Visual Studio. Here inside of Visual Studio, I want to demonstrate the capabilities of the task class using a simple console mode program. Inside of the main method, this console mode program is going to call into a slow operation. That slow operation is going to take at least 2 seconds to complete thanks to the thread.sleep call, and then it's going to return a 42. In between, it's also going to print out the managed thread ID that started the operation and the managed thread ID that is executing when that method finishes. Then back in the main method, after the slow operation is complete, we'll print out the numbers from 0 to 9, show the slow operation result, and finally print out a message that we're complete and also show that thread ID. If I run that program right now, it's probably not surprising that we first have to wait for that slow operation to complete, then we can print out our numbers, then we can show the result, and everything happens on the same thread. The managed thread ID is 1 the entire way through. So let's change this around to use a task, because perhaps we want the slow operation to execute in parallel while we're printing out these other numbers, and that represents other work that we have to do, other processing that has to take place. And so what I'll do is I'll use the task class to create a task out of the slow operation. And that's as easy as going to task.factory, telling it that it needs to start a new task. This task will return an integer, and the work that we want represented is this slow operation. So it's going to turn the work that needs to be completed to finish that method call into a task, and I'll change this from result to task. Then you might ask, how do we get the integer return value? That's as easy as saying task.result. Now, if the task is not completed at this point, then task.result will block the program at that point. It has to wait until the task completes before it can give you that integer value back. But there's other things we could do with the task. So while our other computations are happening, we could also walk up to this task and see if it's canceled, if it's completed, if it's faulted. We could also tell the task to continue with some other action and make that into a task, so we can chain a series of these tasks together to get them all to operate serially. But for right now, we'll just leave it with task.result. That will block right here and give us the result. And if I run this now, what we should see is that we can start printing out numbers while the slow operation is working. The slow operation is on a different thread now than the thread that's executing inside of the main method. The slow operation was on thread 3, the thread inside of main was on thread 1, and we still get the proper result, which is 42. That's a quick and simple demonstration of what task can do for you. We never had to worry about scheduling threads or starting a thread. It all just happened behind the scenes through this abstraction called a task. And next, we'll see how the C# compiler here in Visual Studio 2012 can make this even more interesting using the async and await keywords.